For millennia, humanity's relationship with light was simple. Fire, then oil, then electricity coursing you through a filament, illuminating our nights. But in the grand tapestry of human innovation, some breakthroughs arrive not with a flicker, but with a silent, profound revolution. A revolution powered by semiconductors, promising efficiency, longevity, and a spectrum of possibilities. We live in an age bathed in LED light. From the smallest indicator on your charger to the expansive displays of our cities, these tiny diodes are ubiquitous. Red and green LEDs emerged relatively early. Why? Transforming everything from calculator displays to traffic signals. But for decades, a crucial piece of the puzzle remained elusive, stubbornly refusing to yield its secrets. A color so fundamental, its absence rendered the full potential of LED technology almost entirely out of reach. Making blue LED, it seemed, was almost impossible. The story of the LED begins in the early 20th century with observations of electroluminescence. But it wasn't until the 1960s that the first practical, visible light-emitting diodes arrived. Nick Holland-Yak Jr., working at General Electric, developed the first red LED in 1962. It was a marvel of its far more durable and efficient than incandescent bulbs for specific applications, though still are relatively dim. Soon after, green LEDs followed, using different material compositions. These early breakthroughs were significant, paving the way for digital displays and indicator lights. Yet, the dream of true, full-color LED illumination remained distant. To achieve white light or any arbitrary color, you need three primary colors: red, green, and blue. Without blue, the palette was incomplete, limited to a narrow spectrum of warm or cool hues, but never the vibrant, full-spectrum light we now take for granted. The challenge of the blue LED wasn't just a matter of finding the right shade, it was a fundamental material science problem. LEDs work by combining electrons and holes within a semiconductor material. When an electron drops into a hole, it releases energy in the form of a photon light. The color of this light is determined by the band gap of the semiconductor material. Essentially, the energy difference between the electrons and holes. A larger band gap produces higher energy photons, which means shorter wavelengths like blue or ultraviolet. For red and green light, common semiconductor materials like gallium arsenide phosphide GaAsP and gallium phosphide GaP worked well. But for blue light, a much wider band gap was required. Scientists identified gallium nitride, or GaN, as the most promising candidate. However, GaN was notoriously difficult to work with. It's an incredibly hard, stable material, but its properties posed immense hurdles for crystal growth. Growing high-quality GaN crystals was like trying to build a perfectly smooth wall on a crumbling foundation. There was no readily available substrate material that perfectly matched GaN's crystal structure, leading to immense strain and countless defects. These defects acted like short circuits, preventing the efficient emission of light. Furthermore, even if high-quality GaN could be grown, introducing the necessary impurities to create the type layer crucial for the LED's function proved incredibly challenging. The atoms wouldn't incorporate properly, or they'd be compensated by other defects, rendering the material useless. For decades, the consensus among many leading researchers was that a high-efficiency blue LED was virtually impossible. While many had given up, a few relentless pioneers refused to accept defeat. Among them were Japan's scientists Izumo Akasaki and Hiroshi Amano at Nagoya University, and perhaps most famously Shuji Nakamura, working for a small, relatively unknown company called Nichiya Chemical Industries. Nakamura, often seen as an outsider by the academic elite, pursued the blue LED with a singular, almost obsessive focus, facing skepticism and limited resources. Nakamura's journey was one of trial and error, often working alone in his lab. He experimented with various growth techniques and materials. His first major breakthrough, building on earlier work by Akasaki and Amano, involved using a sapphire substrate, a material that didn't perfectly match GaN, but was at least stable. Crucially, he developed a low-temperature GaN buffer layer, a thin film that allowed subsequent high-quality GaN layers to grow with far fewer defects. This was a monumental step, but the doping problem persisted. The solution to the doping challenge, discovered by Nakamura, was surprisingly simple yet revolutionary: thermal annealing. By heating the GaN material after growth, he found that the magnesium atoms, the type dopant, could be activated, finally allowing current to flow efficiently and light to be emitted. In 1993, Nakamura unveiled a high-brightness blue LED, a device that many had written off as the holy grail of optoelectronics. It was a triumph of perseverance, ingenuity, and sheer scientific will. The invention of the high-brightness blue LED didn't just add a color to the spectrum, it unlocked an entirely new era of illumination. With blue light, it became possible to create white light. The simplest method involves coating a blue LED with a yellow phosphor. The blue light excites the phosphor, which then emits yellow light. Our eyes perceive the combination of blue and yellow as white. This seemingly simple trick transformed the world. Suddenly, we had a light source that was incredibly energy efficient, consuming a fraction of the power of traditional bulbs. It was durable, lasting tens of thousands of hours, and environmentally friendly, containing no mercury. The blue LED paved the way for LED televisions and computer monitors, offering vibrant colors and thin designs. It enabled Blu-ray technology, using blue laser light to add more data from discs. From medical devices to horticultural lighting, the blue LED ignited a cascade of innovation. In 2014, Akasaki, Amano, and Nakamura were jointly awarded the Nobel Prize in Physics for the invention of efficient blue light-emitting diodes, which has enabled bright and energy-saving white light sources. It was a testament to their individual brilliance and collective contribution, acknowledging the profound impact their work had on humanity. The story of the blue LED is more than just a tale of scientific discovery, it's a powerful reminder of human perseverance. It highlights how fundamental research, often dismissed as impractical or impossible, can fundamentally reshape our world. It teaches us that sometimes the greatest breakthroughs come not from vast resources, but from the relentless pursuit of a vision, even when the path ahead seems utterly dark. From a seemingly insurmountable challenge, a single color of light emerged, illuminating our planet, conserving our energy, and inspiring a future brighter than anyone could have imagined. The impossible, it turns out, was merely waiting for someone brave enough to try. Thank you for watching our video. Don't forget to like and subscribe. We value your thoughts greatly. Let us know in the comments.